Good day. So today we will talk about some uh, uh, some protocols which are useful for controlling the network and sort of making machines connected to the network. Specifically under the broad class, we will talk about DHCP and ICMP. So there are some protocols associated with this, so we will talk about those. So DHCP is Dynamic Host Configuration Protocol. Okay, so it is about configuring a host, configuring a machine, configuring maybe a PC or some computer which is connected to the network. Its chief utility, there are other utilities of DHCP, we will come to that later, but then its chief motivation came from dynamic assignment of IP addresses. Now, dynamic assignment of IP addresses is desirable for several reasons. First of all, IP addresses can be assigned on demand. Okay, this may be good. For example, when you have a scarcity of IP addresses, say real IP addresses, in that case, it may be nice that for people you keep a central pool of IP addresses, and then as some as some computer comes online, it assigns an IP address from the pool, and when it goes out, naturally that IP address is withdrawn and given maybe to some other machine. Okay. So that is one good thing about it. Another place where it may be required is that suppose you have some kind of what is known as a RAS or a remote access server, to which a number of machines would connect via dial-up connection. So in that case, you want to give them a temporary IP address for the duration of the connection. Then suppose somebody is visiting some network with a laptop, okay, and the laptop he wants to connect. Now he has to get a network address of that particular network, so that network address has to be dynamically assigned. So IP addresses are assigned on demand. This of course also avoids manual IP configuration, which is prone to errors, and support mobility of laptops. Now, three protocols have been used for this, one after the other, and they have overlapped. Okay, so RARP, which is major use up to 1985, beyond that also people kept on using it, and then BootP, which is the bootstrap protocol, and then currently the DHCP. All right. So DHCP, for example, this DHCP works with a BootP. So if there is a BootP client also, he can then still use a DHCP server, but only DHCP is widely used today. So let's quickly look at this RARP and BootP also. So RARP, actually this is reverse ARP. So address ARP or address resolution protocol, if you remember, that the problem was that given an IP address, or rather given this is for mapping between IP addresses and MAC addresses. So for ARP is given an IP address, what is the MAC address? This I want to this I need when I want to communicate over a LAN. RARP is the reverse of this, that that what is the that this is the MAC address, what is the IP address. Now, why would that be necessary? That would be necessary in case suppose you have something like a diskless workstation which boots over the network. Now, a diskless workstation, of course, it has its MAC address, its own MAC address. It wants to get assigned an IP address. So, that is an example of where RARP is typically used. So, it broadcasts a request for IP address associated with a given MAC address. So, this is just like ARP. RARP server responds with an IP address. Only assigns IP address, not the default router, subnet mask, other things which are required there. That is not a part of this RARP. So, you have this IP address to MAC address, that is ARP, and Ethernet MAC address to IP address, that is the RARP. Next is some improved version of the same thing. That means we want to still assign IP addresses dynamically, is the bootstrap protocol, but it does some more things. Okay. So, host can configure IP parameters at boot time. So, basically this is of three services. One is IP address assignment, second is detection of IP address for a serving machine, and the name of a file to be loaded and executed by the client machine. This is a boot file name. So, that is where this is the source from which it gets its name, bootstrap protocol. So, when the machine is booting up, it not only gets an IP address, it also gets the name of a file which can be loaded and executed. So, that is the bootstrap protocol, or this is also known as bootp. It not only assigns IP address, but also default router, network mask, etc. So, whatever the particular machine requires for communication, and namely its network, that subnet mask and the gateway, etc., that those addresses are given by the bootp protocol. This is sent as an UDP message. So, UDP port 67 for server and UDP and port 68 for host. This port 68 for host, this is required because you may want to, from bootstrap protocol, you may want to find out about a machine which is already there on the network, and use limited broadcast address, that is 255, 255, 255, 255. This address, if you recall from our discussion about addresses, this is a broadcast address where the broadcast is limited to this particular subnet or network. Bootp can be used for downloading memory image for diskless workstation. So, whatever was the motivation for RARP, the same thing can be done through bootp, and assignment of IP address to hosts is static. This is one sort of drawback of bootp. Next, to make it dynamic, we go to the dynamic host configuration protocol, which is sort of become the standard now. So, which is more versatile than RARP or bootp, and it can do a lot of things apart from just giving the IP address, as we will see. So, this was designed in 1993, an extension of bootp, many similarities to bootp, and same port numbers as bootp. So, that is why so if you have some bootp clients, that also the DHCP server can handle. Some extensions, some important extensions, there are a lot of extensions, especially with options, but these extensions supports temporary allocation or leases of IP address. By leasing of IP address, we mean just recall the situation when we have say a remote access server and where people are dialing up. So, what would happen is that would be given a particular IP address for a fixed amount of time, all right, and when its lease expires, that IP address may be withdrawn. So, of course, what would happen is that maybe, and we will come to that, maybe halfway down the lease period, if there is no great demand for IP addresses, then the lease may be automatically extended, or if there is a great demand, the lease may be withdrawn also. So, this is for a temporary period of time. So, that is how it is dynamic. DHCP client can acquire all IP configuration parameters. So, all types of parameters can be had. I mean, so not only subnet mask and gateway addresses, which are also there in bootp, but then there are all kinds of other parameters can also be downloaded from DHCP server. So, DHCP is the preferred mechanism for dynamic assignment of IP addresses, that is one thing, and DHCP can interoperate with bootp clients, and it has a number of options. It is not possible to mention all the options here. Other DHCP information that is sent as an option, so the number of options is actually greater than 100, number of possible options. So, these include things like subnet mask, network server, name server, host name, domain name, forward on off, default IP, time to leave, broadcast address, static route, Ethernet encapsulation, X window manager, X window font, DHCP message type, DHCP renewal time, DHCP rebinding, time SMTP server, SMTP server, client FQDN, printer name. So, you see all kinds of I mean, as a matter of fact, as the number of services grew over as the number of services which are given over a network, as that grew, it became important to give more information to the machines. I mean, originally the machine was just for communicating between two computers, but as more and more services, for example, there may be a centralized print service on the network. So, whenever you want to print something, you fire the print job and it will be done over the network. Similarly, all kinds of other services became available in the local network as well as over wider network. So, as more and more services become available, it became necessary to give this kind of, so all these would require some kind of configuration on the host end, because the host end must know what all are there. So, such information can be transferred via this DHCP. That is the main point. So, DHCP operation, there are a number of them. I will mention them, but describe only a few. Say DHCP discover. At this time, the DHCP client can start to use the IP address. So, it has discovered. Renewing a lease, sent when 50% of the lease has expired. If DHCP server DHCP enact not acknowledged, then address is released. Then the address has to be released. Then you know that your lease is not going to be renewed. DHCP release. At this time, the DHCP client has released the IP address. So, client has given it up. DHCP message header fields. So, some fields there is an opcode. So, either there is a DHCP request or DHCP that is from the client and DHCP reply from the server. So, they have opcodes 1 and 2. No, DHCP message type is sent as in an option. So, what type of message? Hardware type, which is 1 for Ethernet, hardware address length, which is again 6 for Ethernet, hop count set to 0 by client, and transaction ID. This is an integer used to match reply to response if there are more than one requests. Seconds, the number of seconds since the client started to boot. Client IP address, your IP address, server IP address, gateway IP address, client hardware address, server host name, boot file name. There are all these fields are there. What happens is that when client sends the request, it would fill in whatever is known to him. Maybe the MAC address is known to him, so he will put in the MAC address. So, all and other fields he will leave blank. So, that is the message he will broadcast. The DHCP server will pick it up and then fill up all the other necessary fields and then broadcast it back. So, these are all the different DHCP message types, like which is there in the option: DHCP discover, DHCP offer, DHCP request, DHCP decline, DHCP acknowledge, not acknowledge, DHCP release, DHCP inform, and so on. Okay. So, having discussed about DHCP, our next topic is ICMP, Internet Control Message Protocol. Now, it is necessary because internet is of course based on the internet protocol. Now, IP protocol has some drawbacks. One of the main drawbacks is that is a best effort delivery service, but it lacks error control and lack of assistant mechanisms. Okay. The point is this, that since this IP is a best effort delivery, it is understood that at some point of time the effort may not be enough, and routers or other nodes on the network may have to drop packets, or packets may not reach its destination in time, in proper order, etc., etc. That may happen. Okay. But the so that part is accepted. But then if that happens, does the source get to know? Because if it first of all there is no error control, and secondly if such errors do occur, there is no message to the sources. Okay. So that is one thing. So that is a lacuna, and secondly there is a you want to control the network for some reason. For example, maybe the network is getting congested. Okay, so you want to do something about it, you want to tell others something about it, but IP does not have the mechanism. So for all this purpose, this ICMP was brought in. So what happens when something goes wrong? What happens if a router must discard a datagram because it cannot find the route to the final destination? What if the time to leave field has a 0 value? What if it has to discard all fragments because not all were received in a predetermined time limit? So in all these cases IP has to discard a packet, and similarly then there are other situations. For example, maybe it has reached the destination but the port is not available. Okay, things like that. So IP protocol also lacks a mechanism for host and management queries. So ICMP was designed to compensate for these deficiencies. So ICMP has a type field, its message type is a type field, indicates the type of ICMP message being sent, and the types we will come to that, it may be queries or it may be errors. Code field gives further information specific to the ICMP message. So for example, for an error, what kind of error it is? Checksum field used to verify the integrity of the ICMP data. So once again a checksum is included to control the error. So these are as I was saying, the type of message. There are two types. We have the ICMP message, we have error reporting, and we have some query response kind of thing. So if there is some error, so this kind of this type of ICMP message would be generated, and if there is a query, another type of ICMP message would be generated. So error reporting. By the way, there is no effort in ICMP to correct the errors. Okay, that is the job of some other layer. Okay, so maybe that is taken care of, as we will see, that is taken care of when we handle TCP. Okay, or maybe some other higher layer protocol. But the point is, so it does not try to correct the errors; it merely reports the errors. Okay, and error messages are sent to the source. So whatever be the, suppose a datagram has been sent and something has happened to it, whatever. So that, and that is because of that some error has occurred. So that message, so whoever drops that packet, he generates an ICMP message back to the source. So that may be a router on the way, that may even be the final destination. So these are various types of errors. So in error reporting, let's say there may be destination may be unreachable, there is a source quench, sending too fast. We will look a little bit into the details of some of the important ones. Time exceeded, some parameters problem, or a redirection. So these are basically some of them, they are by no means all. Okay. But please note that no ICMP error message will be generated in response to a datagram carrying an ICMP error message. That means that whoever somebody has generated an ICMP error message and it is travelling back to the source, and that itself gets an error, that itself may have to be dropped on the way or something. In such cases, we do not generate another ICMP message. Okay, quite a bit of problem happens due to maybe congestion of network. So, if the network is very congested, many packets may get dropped, and then if in response to dropping any packet you generate more packets, then the congestion is not going to go away. So, ICMP error messages do not trigger other ICMP error messages. For a fragmented datagram, that is not the first fragment. For example, a datagram may have been fragmented into a number of parts, maybe say maybe 50 parts. Now, for each of them you generate an ICMP message, then the ICMP messages would be too many. So, so it is only generated for the first fragment. For a datagram having a multicast address, once again this is I mean we cannot send ICMP messages to all members of the group, and for a datagram having a special address such as this loopback address or some address like that. So, no ICMP error messages are generated for these. So, all error messages contain a data section that includes the IP header of the original datagram plus the first 8 bytes of data in that datagram. This information is required so the source can inform the protocols about the error. What would happen is that from the original packet which was, let us say, dropped, from that the IP header is sent back, so that you know that first of all you have to know that to which machine, which is the source, where do you want to send back this ICMP message, and secondly, even after this ICMP message gets back to the specific machine from which the original packet had generated. So, at that point this may have be some error message due to the network, intervening network, maybe the network is too busy or congested, or this may have to do something with some process or application which is running on the source machine. So, now so after getting that message, it must know to whom to tell, that host machine must know that to whom which process this relates to. So, that is why some part, the initial part of the original datagram, that means the IP header of the original datagram plus the first 8 bytes of data in that datagram. You would understand that after the IP header what comes is the transport layer header. So, the part of the transport layer header also goes into the goes back along with the ICMP message. This information is required so that the source can inform the protocols about the error. Now, one type of error message is destination unreachable. When a router cannot route a datagram or a host cannot deliver a datagram, in that case the destination is unreachable. A router cannot detect all problems that prevent the delivery of a packet. So, it is not always possible to exactly know why the destination is unreachable, but at least this information that the destination is unreachable, that goes back to the source. Source quench. So, this is a crude attempt to implement some kind of flow control. IP protocol has got no flow control. Routers and hosts have limited size queues. So, what may happen is that maybe in an intermediate router a number of packets have come up, suddenly there is a flood of packets into one intermediate router from various directions. So, what will happen is that its buffer is going to overflow, it will not be able to process, because there is a limit depending on the speed of the router, etc. There is a limit how fast packets can be processed and forwarded by an intermediate router, and if other packets keep coming in within that time, they are going to be stored in the buffer. Now, the buffer might overflow. In that case, there is no other way but to drop those packets, that router cannot do anything. So that is this thing. So what this router desperately wants to tell other people in the network is that please slow down on sending packets, I cannot handle it, I am overwhelmed. So he is basically trying to slow down the this thing, so slow down the message, slow down the flow of packets into itself. So it sends a source quench ICMP message towards the sources. So routers and so if datagrams are received faster than they can be processed, the queue may overflow. So in that case, it asks this thing to slow down. If a router or host discards a datagram due to congestion, it sends a source quench message to the sender. The source must slow down the sending of datagram until the congestion is relieved. This may be used when bottlenecks occur, for example, on a WAN link with too much congestion. It used to reduce the amount of data lost. Now warning, source quench messages will in turn generate network congestion, because there were already too many packets in the network, but you have sent a source quench packet towards the source. So what is going to happen is that in the router immediately before I mean in one, which is just one hop towards the towards the source, he will get, he was already getting packets from the source, and he will also get an ICMP message from the router just one hop down. So he is now having more packets. So this way actually what will happen is that congestion might travel towards the source, but anyway after finally it reaches the source, that source will hopefully slow down and all this will die down. Time exceeded. Whenever a router receives a datagram with a time to leave value of 0, that means it has been going around the network, it discards the datagram and sends a time exceeded message to the source. When the final destination does not receive all of the fragments in a set time, it discards the received fragments and sends a time exceeded message to the source. So these are two different cases. One is that in the destination all the fragments did not reach, some of the fragments never reached, so there was a specified time after which it has to drop all the fragments and sends a time exceeded message to the original source. And the other thing is that when a router receives a datagram with a time to leave field which is 0. By the way, if you remember this keeping a time to leave field and decrementing it at every hop, this is quite important, because suppose there were some packets which were sort of floating around in the network, and due to some trouble with the routing tables, a loop has been formed. So what is going to happen is that if you do not have this time to leave field, this will go round and round and just keep on ad infinitum. So they are going to slowly burden the network. So the solution to that was that after a certain number of hops, the packet is dropped. So what is done is when the packet is dropped, a message, time exceeded message, is sent to the source. There may be parameter problems. If an ambiguity is found in the header of a datagram, the datagram is discarded and a parameter problem message is sent back to the source. Redirection. A host usually starts with a small routing table that is gradually augmented and updated. One of the tools to accomplish this is the redirection message. So this helps in routing actually. Now let us come to queries. ICMP can also diagnose some network problems. For example, echo request and reply, timestamp, address mask, router solicitation and advertisement. So these are examples of queries. We will just see a few of these also. Echo request and reply, this is used very often when you want to find out whether a network is up and running or not. We will come to this in more detail later on, but here an echo request message can be sent by a host or router. An echo reply message is sent by the host or router which receives an echo request message. The echo request and echo reply message can be used by network managers to check the operation of the IP protocol. Echo request and echo reply message can test the reachability of a host. This is usually done by invoking the ping command. We will go to the more details of ping etc. trace route later on, because that is one kind of command which even users quite often require. For example, you have logged on and now you find that you cannot reach anybody. The network is not, I mean, some address that you want to reach, it is not coming at all. So now where is the problem? First of all, maybe you want to find, is the problem in your local network, is the problem in the maybe in the local subnet there is a gateway. So you might ping that gateway to see whether you can reach up to the gateway. If your ping message goes up to the gateway and then an echo reply comes, then you know that up to that much the network is okay. Then maybe you then for the entire network you may want to ping the router, whether you are okay up to the router. If you are okay up to the router, maybe the problem is somewhere in the link outside. I mean, the problem may even be in the right in the destination which you are trying to reach. So one way to go on probing the network even by users is to use ping. So we will see a little bit more about ping later on. Later in this lecture. There is a timestamp request and reply. Timestamp request and timestamp reply messages can be used to calculate the round trip time between a source and a destination machine, even if their clocks are not synchronized. So sending time is equal to value of received timestamp minus value of original timestamp. So this way you can get some idea about the round trip time. There are other ways we will see. So receiving time is the time the packet returned minus value of transmit timestamp. Round trip time equal to sending time plus receiving time. So the timestamp request and timestamp reply message can be used to synchronize two clocks in two machines if the exact one-way time duration is known. Address mask request and reply enables a host to request and receive the network or subnet mask, useful for diskless stations at startup, but we have seen that DHCP is another way of handling this. Router solicitation and advertisement allows for request of routing information and the reply of this information. Routers can periodically send router advertisement without being solicited. So what happens is that suppose a router has just been connected to the network. Now you remember that routers have to run the routing protocol, whatever it is, say RIP or BGP or OSPF, whatever it is. So that means it needs to talk to its peers, it needs to talk to the other routers. Now, but how will the other routers know that a new guy is in the block? That means the new router has been connected to the network. So one way is that as soon as the router gets connected, it does some router solicitation and advertisement. It advertises itself, okay, I am here, I am here, so that other people get to know that he is here, and slowly the entire network becomes aware of this new router which is connected. Okay. And similarly, say a link may go down and all kinds of other things may happen. So this router exchange of router information, that has to happen through some mechanism. So this is one. Router discovery message. Host can learn about available gateways to other networks. Host send a router solicitation message to begin the process using the multicast address of 224.0.0.2 as the destination. May also be a broadcast message in case a router does not accept multicast messages. When a router receives the message, it will advertise its available gateway. And finally, the checksum of the ICMP message. In ICMP, the checksum is calculated over the entire message, that is the header and data combined. This is just to keep some control over errors. Clock synchronization. Software may require time synchronization. So ICMP timestamp message combat this problem, as we have already discussed. Allows local host to ask for current time from remote host using
ICMP timestamp request. So type 13, and then remote host uses ICMP timestamp reply, which is type 14. So better way of synchronizing clock may be to use network time protocol. That is a different thing, we are not discussing it here. And the time is the UT, the universal time. Now a little bit more about ping and trace route. These, so as an overview, I mean, and of course this is a part of the ICMP messages, but since these are so useful, I thought that I will just discuss it specially a little bit. So ping sends an ICMP message to a remote host and lets you determine if that host is responding. Actually ping uses that echo and echo reply for this, that ICMP message. And trace route uses TTL fields to query all hosts en route to a specific destination. You can use trace route to map a network. That means you want to know which is the route you are tracing. I am coming to it. Now let us first talk about ping. It is named after sonar. You know, in sonar you want to probe some place, so you send an ultra sound signal just like you do in a radar, and if it bounces off something you get a ping. Okay, so that is where the name comes from. So you want you send an echo request and you expect an echo reply, that is your ping. So server normally implemented in kernel uses ICMP echo and echo reply messages. On Unix, the identifier field is set to Unix PID of sending process. Sequence number starts at 0, incremented every time a new echo message is sent. Actually what happens is that usually, I mean of course you can configure it, that when you ping a machine, not just one request is sent, because think about it this way, the machine you are trying to ping, that channel may be noisy. Okay, if that happens, your echo request or the reply may get dropped in between. So sending one request was not thought sufficient. So maybe 3 times or 5 times you can sort of configure it. It sends echo request and it expects all the 3 or all the 5 replies. Maybe it receives none of them. Okay, so in that case it will say that okay, 100% packet loss, or it will just get maybe 2 out of 5. So it will say 60% packet loss and 40%, and this is the time. I will show you one example of a ping. Suppose we have a ping the machine 144.16.192.182.1. Okay. So we have pinged this machine. I simply say ping and then give the IP address over here. By the way, you could also use if you have a name server on the network, you could also put a name over there. Anyway, ping 144.16.182.1, 56 data bytes, that is your data, plus it will have something, we will come to that calculation later on. So you may get a result something like this, 64 bytes from so this is the I mean this is what you are getting from the echo echo reply. So 64 bytes from 144.16.182.1 ICMP sequence equal to 0, time to live is 240 and time is equal to 37 milliseconds. So it gives you some idea about how much time it takes. I will come to that. So then another packet has come back as an echo reply, 64 bytes from the same machine, sequence number 1, and time is so much. And at the end of all this, so for each packet that it receives back as a reply, it is going to print a line like this. And then finally it will give you a statistics. Maybe it will something like this, is 13 packets transmitted, 11 packets received, which means that it had originally sent 13 packets and it got only 11 packets back, so 2 packets must have got lost. Okay, so 15% packet loss, and round trip time you may the mean average max, so maybe it can so from the ping you can get an idea about the round trip time. So, this is one answer and some details on the output. Sequence number is shown for each message. In our example, message returned in order, but we lost some packets. The returned may be out of order also. TTL field of return message is displayed, and round trip time is calculated at the host based on the sequence number. So, we can estimate the bandwidth also, not only the round trip time, we can try to use for, that means of course this works only for a few hops. Okay, if it is beyond a number of hops, your ping will not work, but anyway the ping packet, so it can estimate the bandwidth. 20 byte IP header, let us say, what is the total. So, 20 byte IP header, 8 byte ICMP header, 56 byte message. This can be set by the user. So, total datagram size is that, so 76 plus 8, that is 84 bytes. So, 84 bytes was sent. Now, PPP, suppose it was sent through a PPP, so it will add about 8 bytes for total size of 92 bytes. So, this connection looks like, so 92 divided by 0.180 by 2, that is about 1069 bytes per second. What is this 0.180? So, if you so this is so 92 bytes. So, this is maybe time, all right. So, this gives you some idea about what kind of bandwidth you are having, and maybe as you can see, then in this particular case the bandwidth is not that much, so only about 1069 bytes per second, all right. So, you may do it, this is a very crude estimate, but you can get some kind of feel about your immediate locality. Now, there is a record route option. Most ping implementations provide record route, which is say -R option on -R option on Unix, Linux, and -r option on Windows. Each router stores its address in the IP options field. Only 9 addresses are possible. Thus, round trip record only 9 possible, and only possible for 4 routing hops. So, you can take only 4 hops, and in but within that time, within that 4 hops, you can find out that how your message went and how it came back. Okay, maybe it went and came back through different paths, it could be, or maybe it took the same path, etc. You can actually trace the route. Of course, as you see that because of the limitation on the size, that is because on the number of addresses that you can store, you can only route or map the network in your immediate locality. So, if you want to go beyond this, then you have to use something else, and we will come to that. That is trace route. So, trace route uses a sequence of ICMP messages to determine the current route to a particular destination. So, how? So, this is actually done in an iterative fashion. So, what I will do is that, suppose I want to trace route to a distant machine, I know its IP address. So, what I am going to do is that I am going to send a message to that machine, but maybe put a very small number for the time to live. So, what is going to happen is that my message will take so many hops, and then its time to live, it has not reached the destination. So, it is somewhere, it has just started maybe towards the beginning. So, its time to live is going to become 0. So, as soon as the time to live becomes 0, the intermediate node, maybe that router, so what it will do is it will have to drop the packet, and it sends, if you remember, it sends an ICMP message back to the source. So, now my program catches this ICMP message and okay, that was on the way. So, it now sends maybe the same dummy message to the destination after increasing the time to live by 1 unit. So, now it is going to get past that router which had in the previous instance dropped the packet. So, it will go one more hop and then the packet will get dropped. So, that router is now going to send an ICMP message back to the source. So, we will know that okay, after this router, that is the router which had that is on the way. So, in this way, one by one iteratively you keep on increasing the time to leave, and that way you route the trace the entire route, you map it out. But one small question, what happens when it reaches the destination? Well, when it reaches the destination, at that point what is done is that this message is sent to a very unlikely port, a very randomly selected unlikely port. So, most probably the destination machine will not know about this port. So, it will say that port is unreachable, and then that ICMP message will come back and we know that I have reached my destination. So, this way one by one I have traced the entire route from the source to the destination. So, this is how it works. Traceroute uses a sequence of ICMP messages to determine the current route to a particular destination. The TTL specifies the number of hops a message can travel. Traceroute sends UDP datagrams while varying the TTL. The router that drops the UDP packet replies with a time exceeded ICMP message. The endpoint will not reply with that ICMP message because it has already reached the end. So, traceroute sends to an unlikely UDP port, eventually get a no such port ICMP message. It knows that it has reached the end. So, and you can see about the ICMP messages. So, this is the reference. Actually, these protocols in internet control message protocols, there are a number of others which we did not discuss, we just discussed a few of them. And then there are some protocol like DHCP, BootP, RARP, ARP. These are also there in the stack, as you will find out. For example, ARP, we talked about these, they help in running the network in a better fashion. So, we have ARP protocol which is a low level protocol, we have this RARP, BootP, ICMP, RARP, BootP and DHCP, that is for assigning networks. Then is ICMP which helps in controlling the network operation and giving error messages. And then there is another side protocol which we will discuss in the next class, namely IGMP, which is for Internet Group Management Protocol. So, that is another part of routing that we have not discussed as yet. So, we will take it up in the next class. Thank you.